Mr. Jeff Lovin is the Senior Vice President and Managing Principal of the Government Solutions Market at Woolpert. He has spent his entire 30-year career in the geospatial profession at Woolpert, and he's developed a diverse technical background as well as project management skills, senior leadership experience, and advocacy experience. Mr. Lovin, cheatgrass mapping using airborne imagery and Lidar. Take it away.
All right, thanks, Ryan. Okay, so cheatgrass mapping in Kentucky. So this project I'm going to talk about, this initial pilot project involving cheatgrass, was just being wrapped up about the time we were kicking off the project this spring for PDS. And so I was sharing this unique story there with Tricia. So, and she says, you have to present this at the GIS conference. And I said, really, Wyoming cheatgrass? She goes, yes. So there you go. You can blame Tricia for me talking about cheatgrass out west to the Kentucky GIS conference. But I'll get to it at the end. What we're doing here is very applicable to other features. So cheatgrass mapping. So what I want to talk about today is the background of this project, how it came to be, talk about the data itself, the process, the method to the madness, talk about our results and accuracy, and then give some conclusions and recommendations moving forward. So the background on this project. So it's really interesting. We've been doing LiDAR since 1999. And I've been doing a lot of LiDAR the last 6-7 years because of the 3DEP program with USGS. So we've been doing LiDAR all around the country, a lot of statewide collects, and had been talking to Karen Rogers at Wyoming about a statewide LiDAR plan and their wishes to move forward a statewide LiDAR program. So we were obviously trying to help out with that. From a cost share funding cycle, partnership with USGS and other federal partners, et cetera, which, proud to say now, we are flying the entire state. Should be pretty well wrapped up here by the end of the year. But this is a year ago. And when these discussions first started happening. And I went to visit both the federal legislators and state legislators to talk about the benefits of LiDAR, why they should do it, why they should fund it. And I met with Congresswoman Cheney in DC. And as soon as she hears just enough about LiDAR and mapping, obviously she wasn't an expert, might have been the first time she heard about it. She says, oh, hang on a second. She goes, can this stuff help us with cheatgrass? Can you map and find cheatgrass? And I said, well, not sure. Being from Ohio, I'd never heard of cheatgrass at the time. So I said, tell me more. She did a great explanation explaining that cheatgrass got its name from the Native Americans because it comes up very early in the spring. Like just as snow melt is happening, cheatgrass starts growing. So in that kind of arid steppe climate out there, what happens is the cheatgrass then takes all of that early spring snow melt moisture that's needed for the prairies and so forth, and it takes all that early water out of the soil. And then by July, it dies, right? It goes dormant and dies. So what you have is a bad situation of starving out native grasses and plants in the spring, and then by July, it dies and becomes fuel for wildfires. So this is a problem I found all over the West. A big part of some of the problems they're having out there is from cheatgrass. So, so my comment back to the Congresswoman was, we map crops back here in the Midwest, different types of crop types. We do a lot of forestry applications with LiDAR and imagery. All plants have their own spectral reflectance. So I think, yes, we probably can map cheatgrass if we get the information and educate ourselves on it. So immediately walked out in the hallway and said, hey, called our scientist, Dr. Ngori, Daniel Ngori, UK grad. And I said, hey, Daniel, can we map cheatgrass? And he says, well, probably. And I said, well, we need to find out. So at that time, we were literally wrapping up a big project in New Mexico who has cheatgrass. And we did a small pilot there just to start getting our head around the whole idea of how we would go about it. And then what I'm talking about today is the actual pilot we did in Wyoming. So we went ahead and did a pilot in Wyoming to see if, in fact, with 4-band color imagery and LiDAR, if we can detect and map out cheatgrass. Here's an image of it, so here it is early in the spring. And of course, as I mentioned, becomes a huge problem when it dries out and dies. These vast areas of it become fuel for wildfires. So as with anything in our world, it's all about the data. So what is ideal, what is needed to do this type of work? We need at least QL2 LiDAR data, which is what is being collected for all of Wyoming, except there's a nice size area in Yellowstone we're doing at QL1. So we do need QL2 or QL1 LiDAR, QL2 or better LiDAR, and imagery. That's critical. We need the imagery for this. And that's where we were in a unique situation. We have the Leica terrain mapper LiDAR systems. And at the time of this project had the first 3 in the world. No one else had them yet. And these LiDAR systems have a integrated medium format 4-band camera. So we are able to collect imagery simultaneously with the LiDAR. And that is one of the things that, thankfully, I said, that is such a cool feature. Let's really test it, right? We had no need. USGS does not require us to deliver imagery of any kind, right, with 3-depth. So I said, hey, if we're collecting LiDAR, just turn those cameras on and have them on. So thankfully, we'd said that. So we were already collecting LiDAR, the first eastern side of Wyoming at this time. And thankfully, we had those cameras on. So we did have 4-band imagery with this LiDAR. And then with anything you do where you're doing stuff with spectral reflectance, doing any kind of species type work like this, you need ground truth data. So again, this is very impromptu, right, from these conversations. So our surveyors were still doing the ground control for this LiDAR project that we just started. So we armed them with some spectrometers, educated them, sent them plenty of pictures, information on what cheatgrass was. And luckily, these guys are at our Denver office. They already knew. And we had our surveyors out there doing ground truthing while we were collecting LiDAR data. So those are key components, obviously. QL2 or better LiDAR, 4-band imagery, and some ground truth data. Here, these colored areas, the green and purple and red, those are the areas that were being flown at that time. So it was the very first small block of data we were collecting. First task order. USGS has broken this up over 5 task orders based on funding and funding partners across the state. So this was the very first task order. So in that area is where we're collecting data. And here are the areas. Obviously, this is kind of a free, gratis pilot that we were doing to see, just to prove to ourselves, not only the state and the Congresswoman, if we could do this. But these are the 3 small areas we picked. You'll see they're all conveniently right along, 2 of them are right along the interstate, so easily accessible. Here's the first one. So this is just on I-25, so heading from Denver up to Cheyenne and on up. I think it's north of Cheyenne. This is just south of Chugwater along I-25. It's the first 5 square mile area we selected. Second area. Okay, now we're getting into some differing terrain, which cheatgrass will grow on certain sides of hills versus the others based on sunlight and so forth. So this is area 2 in Platte County. Moving on up, and last area is 5 square miles northeast of Lusk, Wyoming. So these are the 3 areas we picked, all easily accessible by road with our surveyors. They were already, again, we were not getting paid to do this. We tried to figure out how to do it as quickly and easy, not to hinder the schedule of the ground control collection and so forth. So those are the 3 areas we selected. And here, again, while they're doing the field survey, this again, right is on I-25. These are some of the ground truth areas we selected. Again, very easy for these guys to get to. Areas where we knew for a fact where it was cheatgrass. Again, here's another good image of what it looks like. A lot of it grows right on the edge of the road, conveniently for us for this pilot test. So it's an idea of what it looks like. There's an aerial view of the area that we've highlighted there. So how do we go about doing this? So of course we acquire the data, and then a lot of this is done through deep learning, right? Through AI, artificial intelligence and deep learning, where we actually, Daniel Ngori and his team actually write algorithms, right, that take into effect slope and aspect, right? Because again, it grows based on certain slopes and aspects. It grows between certain elevations, 2,000 and 10,000 feet is where it seems to grow. And it's in sagebrush and these steppe areas, right? So these high plain areas with sagebrush. So we basically, when we build the algorithms, when we train these algorithms, right, we build in all of these things, right? So then we go through, and of course, through that process, delineate relevant data. Right, so it's all about the time of data collection. We have our field survey for reference data. And then again, you just basically run an algorithm, check results, fine tune it, run it again. So you're training these data sets, if you will, right, as you go. This is more detailed. I won't go into it, but this is more detailed. Basically how you train the classifier, classify the image, output the results. And you just keep building upon this until you refine it. And again, this is where the ground truth data comes in so critically important, right? To check your final results against the ground truthing. So again, we use the IR band from the imagery. This is our initial spectral analysis, just looking at spectral reflectance. So you get a lot of false positives, as you can see. And then we narrow that down through the process we just highlighted. And what we have here is a heat map. So the areas in blue are your low probability, whether it's pavement or grass, bare earth, what have you. And then what you start getting into is really the yellow, but the orange and red are where the much higher probability. Red being almost for certain that those areas are cheatgrass. And this is actually a look of the deliverable. The state has finally settled on these heat maps are what we're going to be delivering them. Another thing that I think I left out was that we also do put in the average, basically built into the algorithm, also the average height of these plants, 12 to 18 inches. So typically we're doing that with canopy heights of forested areas, but the same algorithm, but we just tweaked it and looked to say, look, let's look at plants at this 12 to 18 inch range, which again, that alone gives you a lot of plants, gives you a lot of tall grass. But then you start adding in all those other factors, the spectral reflectance, you add in slope and aspect, all those other things are algorithms that help you narrow it down. So here's just a look at the light point cloud in 3D, one of the areas. Here's a straight down look in 2D. This is showing just that canopy height model, right, where we start putting in. Of course, you've got some anomalies because this is an overpass, so it's confusing the algorithm, right? Those are things that have to be edited out. But you start to see, and again, this could be anything at this point, right? Not just cheatgrass. At that height, within that height model, that height range. So again, here's another heat raster probability map based on our algorithms. Red being where we're most confident that it is cheatgrass. Just coded a different color there. So here's area 2, same results. This is where you can really start to see the slope aspect, right? On the north and east sides of these hills is where you see the most of this growing, which makes sense with the sun. This is the very hilly area. And then here's area 3, much more flat, higher elevation here, but very flat, big open range areas. Here you see it's more tied to some of the actual water, right? Hydrology. Maybe, hopefully you can see it, maybe hard to see, but you got a lot of some relief here. You got some wet areas, you got some swales here, and then you actually have a creek running through here. And as you can see, obviously that's where it's densest, right? It's going for that moisture, which, you know, this is probably a ranch area, so it's a big problem when the ranch grass starts getting choked out by in some of the prime areas here where water with cheatgrass. Here's another zoomed in view. Again, green, dark green being the highest probability areas. So deliverables. So what we've committed to deliver is a 1 meter grid raster showing the probability, low, medium, high. So that's a heat map I showed you. That's one of the deliverables. So let's talk about accuracy. Classification accuracy. We use the simple regression models between the ground truth observation and predicted probability. Horizontal accuracy, well, that's greatly obviously tied to the LiDAR. Horizontal map accuracy is assessed using the root mean square error, or MSEs, and same with vertical, right? So it's all tied to the QL2 LiDAR. So what are those accuracies? So first, for classification from our algorithms, we feel that our cross-validation results gave us about 88% accuracy. We feel, just again, that's our own test against our ground truthing, that overall those 3 5 square mile areas, we hit about 88% on our ground truthing. And then the horizontal accuracy, again, is about 7/10 of a foot at 95%. That's our MSE for the QL2 LiDAR that we achieved. And the vertical wasn't really measured because there's, you know, with the deliverable, there's no real vertical requirement with the final deliverable for the cheatgrass. So conclusions, you know, so this really helped us further refine, right? We've as we further develop our AI catalog, doing this deep learning, building all these different data sets for extracting features, that this could be very valuable for the Western United States. So we're talking to the Western Governors Association. We're talking to some of the other states now, and you know, that this may be a big impetus for funding LiDAR out west, right? That's where 3DEP is. If you look at the 3DEP map, you know, nation's nearly 70% complete. Well, what's not finished are those Western states, many of those big Western states. And part of that is the cost share model. You know, Ohio, Kentucky, Indiana, right? It's easier to fit the typical USGS 3DEP cost share model of, you know, it's about 65% paid by the state and locals, 35% by the feds. Get out west, you know, they don't have that kind of money. They don't have the tax base. They don't have the population. And, oh, by the way, in a lot of these states, the feds own vast amounts of the state with federal parks, national parks, and so forth. So USGS is aware of that. They're talking to new partners like BLM and so forth, and they're very interested in this. So we've done multiple presentations of this to USGS science team and leadership, and this is part of their discussions with BLM, is this ability to map cheatgrass. But also, Wyoming, we're already doing another pilot for a 2 other invasive species, Medusa head and Vignata. So we're doing 2 other pilot projects already. One's up in Sheridan County, Wyoming. So again, this, and there's the conclusion too, is that today I'm talking to you about cheatgrass. You know, we could do a different plant in Eastern Kentucky probably. But also this can be used for everything from pavement, pervious surfaces, buildings, any kind of vegetation, any kind of, you know, planimetric features. We're doing a lot of our this same deep learning AI is what's being done for Northern Kentucky PDS, right? We're extracting hydrologic features, 3D, USGS 3D derived hydro, and planimetric features using this same AI deep learning technology. So, so it's pretty exciting being an old photogrammetrist where most of my career, this was done manually and done in 3D. And we still have to QC that way, especially when you're talking like 3D hydro or some road features. There's still some cleanup and manual editing in all of this. So this isn't totally automated, but it has greatly improved the efficiency and has greatly brought down the cost of extracting critical features, whether it be from pavement to cheatgrass to hydrology, basically you name it, any mapping feature that you can think of, which you need to categorize, land use, what have you. So again, this has just been a very unique project for us. One of those things is often you stumble into it. When I look back at what has been the drivers to fund LiDAR projects across the country, up in Maine, a big thing was vernal pools, mapping and finding vernal pools. Another thing I wasn't very familiar with being from Ohio, but it's these, this karst topography, which, the part of Kentucky has a lot of this, and the cave areas as well, limestone karst areas. So being able to delineate and find these vernal pools in Maine, they're a huge issue as far as insects, mosquitoes, and so forth. LiDAR is able to do that over vast forested areas easily. Ohio right now, Ohio is updating its LiDAR to QL1 statewide. And the reason QL1, Ohio Department of Natural Resources, is paying for that difference between QL2 and QL1 because they've tasked us with this same technology to map abandoned oil wells. So orphan wells, not Orson wells, orphan wells. So we back in the late 1800s, early 1900s was the last big oil and gas boom in Ohio, and I didn't realize this living there my whole life, but there are thousands of abandoned wells from that time that were never capped or not capped properly. So there's been some injuries, safety issues with that, obviously, but also environmental issues with seepage and different things. So ODNR's had this program of going out, looking at what records they might have had. It wasn't like they had, a great detailed permitting process back in those days. So trying to use all the records they can find, and a lot of boots on the ground efforts to go find these oil abandoned orphan wells and cap them properly. So we've been able to, again, did a pilot like this for Ohio. It was very successful, but that's where in the pilot we said, we don't feel confident of a very high success rate unless we had QL1 data, 8 points per square meter LiDAR. And DNR paid for that because they're paying for it with what they're realizing in savings from having to go out and do this in a more boots on the ground manual process. So yeah, it's pretty exciting again to see how AI and deep learning has moved into the geospatial mapping space and all the uses we're using it for. So from vernal pools to abandoned orphan wells to cheatgrass, all these different drivers and funders to help pay for LiDAR. So recommendations, again, this is specific to cheatgrass. It's as we talked about, it grows very early in the season. We did get some help. It was great having Mr. Martin Hicks from the Wheatland Regional Biologists at the Game and Fish, Wyoming Game and Fish, who that is our client, right? For the Cheatgrass project, our client is Wyoming Game and Fish. We were able to use him. He had a lot of obviously local knowledge, helped with verification and some additional ground truth data, some previous mapping that we were able to use to check against our results as well. So it's been great partnering with him. Again, learned there's a lot of other species out there. So again, we've already got 2 other pilot projects going on to look at those, and anxious to see how those turn out. So with that, that's all I have for you. I think we've got about 5 minutes or so for questions. If anyone has questions.
You had one question from a colleague of yours that sparked a little bit of a conversation. What's the worst invasive species in Kentucky?
Well, I was kind of joking about some illegal species in eastern Kentucky. My reference was, but I don't know. here's
Ohioans was one of the most liked answers on that.
Buckeyes. Hey, I'm just here virtual. I didn't cross the river this time.
Hey, I'm working in Kentucky and living in Ohio. I'm the same as you.
Honeysuckle. Yeah, honeysuckle's a stuff. All right, I'm seeing the chat now.
Asian carp, wild pig.
Asian carp, wild pig.
Caroline asks, how do you find the unique signature of a plant to tell it apart from everything else?
So that's where we research and know from the IR, right? So lidar is a right. It's a near infrared sensor itself, right? So every lidar point, not only is it a 3D point in space, it has intensity values. So whatever that lidar point is on, right, we can basically you can create imagery from lidar as well, right? Intensity imagery. So using intensity values from the lidar, and then knowing the spectral reflectance of a said plant, which has been documented for cheatgrass, for example, right? We know, and I think it was somewhere in here. I don't know offhand the actual number of the nanometers, but there'll be a certain on the spectral scale. There'll be a specific range of nanometers that, and again, it depends on what time of year you're flying the cheatgrass too. Earlier in the spring when it's green, or towards June, July, it turns like a real dark purple almost when it dies. But all that whole range of growth, that spectral range will change. You just have to document and know those numbers, right? So what on that IR band of the imagery, what is that range of nanometers of the spectral scale fits cheatgrass. And of course it may fit other plants that may have similar, depending on the timing, especially earlier. It's better to fly it in that June, July, because it's already starting to turn, right? Or in the spring, a lot of stuff's green, right? So it's either you got to get it really early, which you have to worry about snow, or you fly it June, July. And of course we're flying 20, 30, that was a small area. After that, everything we've flown in Wyoming has been in 30,000 mile chunks. So we're flying it over a broad range of its growth cycle. So we just got to, again, tracking the time of day, tracking the dates, tracking when we fly, and we have to adjust our algorithms accordingly. But yeah, it's that spectral reflectance number. And that's initially done basically on the ground with a spectrometer, right? Going out and taking a physical reading. That's why the ground truthing is so important.
Any other questions? All right, we've got 1 or 2 more minutes left. We'll leave this open. But while we still are under time, I want to thank you, Jeff, for presenting today. I think that was an excellent presentation, and I think you hit the nail on the head when, why are we talking about cheatgrass when that's not a Kentucky issue, but the broader spectrum, it ranges to be able to fit our narrative as well. I think that's a great example of how GIS and how different technologies are improving the way that we work and the way that we can adapt and help our environment and change it if we need to. So thank you very much.
Yeah, thank you. Appreciate the opportunity.
Virtual applause.